Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning. Thanks for coming. It's my pleasure to welcome Ping Tan for the second time. So he visited us a few years ago. So Ping graduated from the Hong Kong University of Science and Technology in 2007, and from 2007 to 2014, he was with National University of Singapore, my alma mater. So now he's with Simon Fraser University. So Ping is very well published in many areas, ranging from computational photography, where he's done video stabilization and so on, image matting, and to low-level vision, physics-based vision, photometric stereo, and so on, and stereo, and now structure for motion, which is going to be talking about today.
Thank you, Sinbin, and thank you all for coming to my presentation. My talk, the title is Director Linear Camera Registration. I changed the title yesterday evening. I think this new title reflects the scope of the talk better.
Oh, I'm sorry. Can I interrupt just 1 second?
Yep.
For those who are watching live, you can actually submit live questions. Sorry about that.
Thank you. So this talk is about structure from motion, which is a technique to recover 3D scene points and the camera poses in 3D space from just two-dimensional images. This is a classical problem in computer vision, and a lot of well-known systems have been developed, including the famous phototourism system. In most of the systems, it consists of the following steps. The first step is a computation of epipolar geometry. Basically, it will compute the relative pose of 2 or 3 cameras according to the feature correspondences in the images. There are many elegant algorithms, such as 6-point, 7-point, 8-point, and 5-point algorithms, depending on the number of feature points they are using. And the second step, I call it camera registration. Basically, we need to upgrade the relative pairwise motion into the absolute global camera poses, including orientations and positions. Basically, we need to put all cameras in a common global coordinate system. Okay? If the cameras are not calibrated beforehand, we still need to do the auto-calibration, but I skip that step because a lot of the modern structure from motion systems are focused on calibrated cameras. So that the last step is the boundary adjustment, which is a nonlinear optimization to fine-tune camera poses and scene point coordinates to minimize the reprojection error. So if we look at these 3 simple steps, the first and the third step are all very well studied with very elegant theories and algorithms. But actually, the second step is often ad hoc and heuristic. In fact, if you refer to this classic textbook of 3D vision, you can find that it describes the second step of camera registration as a black art. So if this is a black art, how do existing systems solve this issue? Let's take this popular incremental structure from motion approach as an example. It will first begin with just a pair of images. Starting from 2 images, with the computed epipolar geometry, we can obtain an initial reconstruction with just 2 cameras and some scene points. And after that, we can add additional cameras 1 by 1, but we cannot keep adding to the last camera because of error accumulation. So usually, after adding a few cameras, we need to perform the nonlinear boundary adjustment to minimize the error accumulation. And then after that, we're going to go through the same iteration of adding cameras and the local boundary adjustment until we finish adding all cameras. We're going to do the so-called global boundary adjustment again to minimize the reprojection error. So that is the typical pipeline of most of existing structure from motion systems. And as we can tell, there are two major drawbacks in this kind of conventional approach. Firstly, it costs the nonlinear boundary adjustment a lot of times, which is going to be computationally expensive. And in fact, we're going to see that usually more than 90% of the computation time is spent on this boundary adjustment. So it's inefficient. And secondly, if we look at the problem from the point of view of optimization, this incremental approach actually fixes some of the cameras before it solving the other cameras. So this kind of asymmetric formulation usually leads to inferior results. So what we want to do is to solve all cameras simultaneously to initialize the boundary adjustment. And if we can do so, the structure from motion pipeline is going to be significantly simplified to have just these three clear defined steps. And this approach is known as the global structure from motion. There has been quite a number of very interesting works. For example, these two methods, they can solve the camera orientations, or sometimes it's referred as the solution of rotations of cameras. They can solve the rotations very nicely, but the solution to the camera centers or translations sometimes get degenerated. This method derives an elegant quasi-convex optimization by minimizing the L infinity norm of the reprojection error. Its result is very strong, but we all know the L infinity norm is sensitive to outlier, so it requires very careful outlier removal to work well on real data. And this work, it combines the discrete and continuous optimization to solve the camera registration problem, but it is limited to cameras roughly on the same plane. This more recent work derived a linear solution for camera translations, yet it is degenerated at a collinear camera motion. Although it sounds like a collinear camera motion is just a special case, but it's actually a very important special case. If you think about street view images captured by a car moving along a street, those images are roughly along a straight line. So collinear motion is an important special case that we cannot ignore. So we derive a direct linear method that has the following interesting properties. Firstly, it solves translation. Secondly, it does not degenerate at the collinear motion. And thirdly, it's linear and robust. So in the following, I'm going to present the detail of our method. So basically for the global method, the input are the pairwise relative rotation and the translation between camera pairs. We use this rotation matrix Rij and a translation vector Cij to indicate the relative rotation and the translation between two cameras. And what we want to recover are the absolute orientation and the position of our cameras. Yes?
Why do you start with pairwise relations rather than triplets?
Good question. Pairwise relations are relatively easier to compute because it requires weaker matching between images. For example, if you start with triplet, that means you have to have sufficient view overlap between all the three images. We're going to come to that later on in the talk.
Because if you don't have view overlap, then the reconstructions are disconnected anyway, so you sort of have to assume that you have it.
Not true, because it could happen that you have view overlap between the first and second image and the third and the second image, but you might not have view overlap between the first and the third images.
I mean, the scales are indeterminate unless there are some points in common, in which case...
You have some points in common,
right.
But the points in common are not enough to determine the relative motion between the first and the third camera in many times. We have examples like that later on.
Okay.
Yeah. Okay, at this moment, let's assume we're going to begin with pairwise motion, all right? So actually, this talk is going to focus on the computation of camera centers. We take this existing method to compute the camera orientations. This method basically takes the Lie algebra averaging approach. Basically, they represent a rotation matrix R by this Lie algebra omega, which is a 3×1 vector. It has a multiplication of the rotation angle with m, which is the unit orientation of the rotation x. Okay, so under this Lie algebra representation, the relative rotation constraint between two cameras becomes a linear equation of the two Lie algebra, and so that they can collect this kind of linear equations and solve all camera orientations in a single linear equation. Okay, so an interesting property is that the camera orientation can be solved without knowing the camera center positions. So this is the Euler approach.
Sorry,
yes?
Theta n is the normal, is the...
N is the orientation of the rotation x.
Right.
Theta is the rotation angle.
Right, so it's the axis angle representation.
Yes.
So you can't directly subtract two of these and have a meaningful relationship, right? You can take quaternion divisions if you want, but you can't just subtract axis angle.
It's actually, yes, you, precisely speaking, you need to take the skew symmetric form of this vector omega,
Right.
and that gives you a matrix. And if you take the exponential of that matrix, it would be the rotation matrix R. Yeah.
Okay.
There's a little more involved math, but this is not our work, and I'm not going to too much technical details of it. Yeah. But anyway, let's assume the camera orientations can be solved. And in the next, we're going to just focus on the camera translations. Okay. Let's first talk about the case of just the 3 cameras. If we have just the 3 cameras, if we suppose 2 of them, their positions are known, we can then calculate the position of the third one by simply intersecting these 2 lines, the relative translation orientations. But in real data, these 2 lines, they are level coplanar, so what we need to do is to take the mutual perpendicular line segment AB and find the midpoint. All right, and then we take the midpoint as an estimation of the third camera. What is really interesting here is that we find the 2 endpoints AB of this perpendicular line segment. They can actually be calculated by these 2 linear equations from the 2 camera centers. And these 2 matrices M1 and 2, they can be pre-computed. I'm going to explain the computation in the next slide. But at this moment, let's just assume they are known. Then under this kind of 2 equations, we will be able to derive a linear constraint between the 3 camera positions. And we can actually obtain similar equations by computing the position, say, of Ci from the other 2 cameras. In that way, we get 3 linear vector equations and for 3 vector unknowns, so that we can solve the camera positions of the 3 cameras altogether.
So there's no consideration of reprojection error here. It's just
We don't consider reprojection. It's all about the epipolar geometry here. So in the next, let me explain how do we calculate these 2 involved matrices M1 and M2. So let's take the M1 as an example. It basically consists of a rotation and the scaling to match the orientation and the length of this relative motion to this one. Okay? And for the rotation component, it can be computed very easily. For example, if you look at a problem in the local coordinate system of this camera, because these 2 orientations are known, so we can determine a rotation matrix to match the 2 orientations. So the rotation is easy. The scaling component requires us to determine the relative length of these 2 baselines. And these can be calculated according to the ratio of a common thin point's depth. We can reconstruct this thin point from this pair of camera and reconstruct it again from another pair of camera, and then the ratio of these 2 depths will give us the ratio of these 2 baseline lengths. So in that way, we can compute the matrix M1. And what is really interesting is that the whole computation of this matrix M, does not degenerate even the 3 cameras are along exactly the same line, because both the rotation and the scaling factor does not degenerate when cameras are along the same line. So this enables this method work with collinear motion. And we actually verified that with experiments. In this chart, the horizontal axis is the smallest triangle angle formed by the 3 cameras. The vertical axis is the position arrow of the camera centers. So we find that even when the 3 cameras are on the same line, our method won't degenerate.
So what happens it just so happens that there are some camera configurations that are pure rotations. So what happens then? Will it blow up?
If some cameras are
Well,
pure
for example, I
rotation.
move the camera and rotate and then move, right? So what happens when I have that?
Good question. I'm not too sure about that. I haven't think about this question.
Yeah, because the projection would just like, will just. I mean, you
It
can't do
might
that.
might not work for this method because it sounds like you have 2 cameras at exactly the same place.
Got rotated.
Yeah, but rotated. So we won't be able to use that 2 cameras at the same location to reconstruct anything point. So that for this method presented here, I don't think it will work.
So in other words, you have to check for such degeneracies, take them out, and then
Yes.
run your method.
Yes, we need to have some outlier checks. Yeah. So in the next, I'm going to generalize this method to the case of multiple cameras. If we have multiple cameras, we can define a graph structure. Well, every camera is a vertex, and the 2 vertices are collected if the relative motion between the 2 cameras can be determined. Okay, we call it a match graph. And we further define a so-called triplet graph, which is a subgraph of the previous graph, and it is formed by triangles glued on a shared edge. Okay, we're going to just look at the biggest triplet graph, and then we can collect linear equations from the triangles in this triplet graph. By stacking all the linear equations together, we can formulate the camera translation estimation as a linear equation AX equal to 0. And we can then solve all camera positions in a single equation. So in this way, we can solve both the orientations and the positions of all camera. Once this is done, we can then triangulate the corresponding feature locations to generate the scene points. So in this kind of structure from motion approach, we actually separate the computation of motion and the structure. We first compute motion, and then we solve the structure. This is kind of advantageous because the motion is usually a smaller scale problem. There are much less parameters involved. So in the next, I'm going to show you some of the results in this method. We first evaluate the accuracy of our method on these 3 data sets with known ground truth camera motion. We compare it with some other recent methods. For each data set, we highlight the result with the smallest arrow in red color. This C is the position arrow in millimeter of camera centers. R indicates the orientation error in camera orientations in degree. So as you can tell, in most of the time, our method will generate the smallest arrow in all the data. And this is another example to verify the computation efficiency of our method compared with the Visual SFM package. So I firstly want to highlight this row. It shows the total computation time excluding the time spent on feature matching and epipolar geometry computation. So as you can tell, because our method is strictly linear, so when the data set becomes larger, the computational efficiency becomes clearer. So on this rightmost, on this Trevi Fountain example, our method is roughly 13 times faster than Visual SFM. And then if we look at the time spent on boundary adjustment, we can tell that for the incremental approach, by the way, VisuSFM is an incremental structure from motion system. So it spends most of the time on the boundary adjustment. All right. And then we compare the number of images reconstructed by both methods, and we find it's rather similar. But later we actually realized this calculation here is biased because our method can only reconstruct a so-called triplet graph. Okay, so at that time, we only take the images in the largest collected triplet graph and throw those images to both systems. And in that situation, they reconstruct a similar number of images. But then we find it's biased. So we actually should throw all images to both systems and see what will happen. And in that situation, actually, VisuSFM is actually better. It will reconstruct over 500 images, and our method only reconstructs about 360 images. So what is the problem involved here? This is actually, we found it's because of the data association. We can only reconstruct cameras in a triplet graph. So what if one edge is missing? What if we cannot determine the relative motion between these two cameras? If that is the case, our method will break the data set into two and generate isolated 3D reconstructions for each of them. That is the problem of the method I just described. And this is due to the scale ambiguity in 3D reconstruction. Basically, the structure from motion algorithm won't know the absolute size of a 3D structure. For example, if we have 3 cameras, it won't know if the 3 cameras form a small triangle on the left or a bigger triangle on the right. So that means if the 2 triangles are connected by a common edge, then we can determine the relative scale of the 2 reconstructions by the shared edge. But if the 2 triangles are only connected by a vertex, we won't be able to determine the relative scale of that 2 triangles. That's why we can only reconstruct a triplet graph in the method we just described earlier. And this happens in real data. So for example, this is some street view images. And as I explained earlier, in this particular case, we can compute the relative motion between these 2 images and these 2 images. But somehow the view overlap between these 2 images is insufficient to determine its relative motion. And in this situation, if we throw these images to the system I just described, it's going to break the data set into 2 and get 2 reconstructions, while ideally we hope to have this kind of result. Okay? And this also happens on internet images. For example, those are the images collected from internet for popular tourism sites. Okay? And to give you a better idea about the data distribution, we visualize the distribution here. Basically, for the popular tourism site, the images are distributed very unevenly. There are some popular viewpoints that has a lot of images, but there are very little image in between. So in a lot of time, we can determine the relative motion between images at a similar viewpoint, but we cannot determine relative motion across viewpoints. And when that happens, the previous method I just described will generate a significant distortion to the final reconstruction. So to address this issue, we might include scene points into the formulation. For example, we might replace the third camera by a scene point P and derive a similar linear constraint about their positions. Well, the slight difference here is that this is a point. P is a point, not a camera. But very interestingly, we can still compute these 2 matrices, M1 and M2. I'm going to explain how to compute them in the next slide. But at this moment, let's assume they can be computed. Okay? If we can compute them, well, this will make it easier to form a collected triplet graph because usually a scene point is visible in many images. So this kind of edges between points and cameras will help us to collect the cameras together. Basically, it will strengthen the collection. and then we can just solve all points and cameras together. It seems like a simple solution to the problem. But, in this slide, I'm first explain how to compute the two matrices M. Okay, they can still be computed if this is a same point. As I mentioned, there is a rotation component. The rotation can be computed as usual. For example, we can look at that the local coordinate system of a camera, and then because this orientation is known, this orientation is known, so we can determine the rotation. And then what about the scale? The scale component can be decided by the midpoint algorithm for triangulation. Basically, for the scale factor, we need to compute the ratio of this length to this one and another similar ratio. These two ratios can be solved by the midpoint algorithm, which basically explore the perpendicularity of AB with respect to this xi and this orientation xj. Basically, we can write an algebraic equation, okay, for these two perpendicularity. And if we look at the local coordinate system of a camera, and if we assume the baseline length here is unit 1, then we can simply write this as this linear equation. Basically, this SI is the ratio between this distance and this one. So when the baseline length is unit 1, SI is simply the distance between A to CI. So the coordinate of A becomes CI plus SI times XI, so that we get this kind of linear constraint. So we can solve the two scales from this linear equation. So, okay, all the matrices can be computed. We can formulate everything together to solve cameras and points together. But there are some drawbacks. The first drawback is that the scale of the problem becomes bigger. There are usually much more thin points than cameras. Okay, the problem becomes a little more complicated, but that is still okay. The real issue is that the formulation I explained just now will introduce some non-existent parameters. For example, if we consider the feature correspondence of these two images, if the feature correspondence is just wrong, then there does not exist such kind of point P that can be projected to the two feature locations. Essentially, we introduce a parameter P that should not exist into the linear system. And experimentally, we found this is very bad. It's much worse than the usual outlier equations. We must get rid of them. So to address this issue, we look at two camera pairs where a single scene point is both visible. And if so, we can derive a linear constraint about that point's location in both camera pairs, and we can then further eliminate the scene point to obtain linear constraints of the camera locations. In this way, this is a linear constraint because the right-hand side of both equations here are linear with respect to the camera locations. So essentially, it gives us a linear equation of the camera centers.
So I guess I'm a little confused.
Yes.
Now, P is seen from CI, CJ, CK, and CL. But you're not linking CI to CK and CJ to CL
yes.
because there's not enough of them? Is that the only reason?
Yes, it's, we don't have to have the link between them. As long as we know this is the same thing point that is visible in all these cameras.
Right. I mean, initially you were describing a problem where they're not the triplets are not there.
Yes.
And then you're saying, as long as there's some point P that's seen by parts that are not triplets, then it's okay.
Yes.
Okay.
I guess the question is, how do you determine it's the same scene point?
Okay, yeah, to determine the same scene point, then you must have some linkages between them. But to derive this formulation, we don't require this kind of linkage. Yeah. Does that answer your question?
Okay, we can talk this.
This equation will be different from different P. So assume you're going to have multiple p's,
Yes.
right?
Yes.
So some of them may be wrong. Some of them might.
You are right. Some of them will be wrong because if it's a wrong feature correspondence, this equation is going to be wrong.
That's right. Even
But-
if you have eliminated p, but the equation could be still.
Yes, but the nice thing is that in the worst case, when this is a wrong match, it only introduces an outlier equation. It does not introduce this kind of non-existent parameter. An outlier equation is much easier to deal with than a non-existent parameter in a linear system. Okay, so essentially, this kind of formulation now allow us to propagate information along a feature track. You are right, actually, we need some linkage between these two cameras and these two cameras so that we know this point P is the same point. So actually, there is a feature trajectory to link them together. And now the formulation becomes that once you have a feature trajectory, then we can relate the scale between the camera pairs along the same feature trajectory. We does not rely on triplet graph anymore. So the formulation becomes that firstly, we're going to collect the feature tracks among the images. And then we can build linear equations from the feature tracks. A long feature track can generate many equations. And the last equation is not a typo. You see this C3 appears twice. Basically, for a trajectory of just 3 cameras, we can basically use the camera in the middle twice to get a linear equation. So this precisely corresponds to the case when we can only determine the relative motion between C2 and C3 and C3 and C4, but cannot determine the motion between C2 and C4. Okay, in that case, we can still obtain linear equations. And then we stack all the linear equations together and we solve them all together to get all camera locations. Okay, yes?
Well, why not just use the triplets? If you have 2 cameras, if you have 3 cameras and they see some points in common,
Yeah.
then you can figure out the relative scale on their translations, right?
Triplets are good, but the issue is that sometimes the data association isn't strong enough to determine the triplet.
The outer 2 cameras may not have actually bundled together or something. You might have said it's not. But as long as the 2 pairwise reconstructions have some 3D points in common, then based on the scale of those points, you can determine the relative scales between the 2. So can't you just get the m's that you need? In other words, even if it's missing, can't you get the scale just from the points that are overlapping?
I'm not sure we
That's the
can.
same thing as your last one, the C2, C3. In other words, why look for quadruplets when you can always just do triplets?
Because in that way, we can only get 2 equations for the 3 cameras. We want to be able to get a third equation, and that is insufficient to solve the system. Yeah. So in this way, we actually can get a stronger constraint.
Because
Than,
the 2 systems that you've reconstructed are
Right.
disconnected by a scale, right? So you
Right.
need 1 equation, so 2 might be enough, right? I don't know that you need 3, right?
I think we need 3. I can go back to that
I'll
slide.
talk to you about it this afternoon. That's
Okay. Let's still resume the talk. We can discuss that in the afternoon. Yeah.
Okay.
So, anyway, now we have a linear equation like that AX equal to 0, and we try to solve it for all camera center positions. And to be more robust, we can actually use the modern L1 optimization technique. We can solve this equation by minimizing its L1 norm. That will be more robust to various outliers, like outlier feature correspondence, outlier essential matrix in the system. So essentially, for the L1 optimization, we need to minimize the L1 norm of the residue vector. This residue is basically this A multiplied with X. And the X is lying in this kind of space omega to avoid the trivial solution X equal to 0. That is our formulation of the L1 optimization. To minimize this problem, we basically take the augmented Lagrange function. This is very similar to the usual Lagrange multiplier. Basically, this is the Lagrange multiplier, and this is a quadratic term. to ensure the convergence region is larger. Okay, and this method can be solved by this so-called alternating direction method for multipliers. Basically, it just iteratively solve all the involved parameters e, x, and lambda one by one in an iterative fashion. And it turns out that e and lambda are very easy to solve, but the solution to x is a little bit hard because we have this constraint on x. So to solve that, we further massage this ADMM a little bit. We linearize the objective function by something similar to Tyner expansion to this kind of way. I'm going to skip most of the math, but in the end, we can get a closed form update for the x so that we can solve all the involved parameters one by one in closed form solution to get all camera centers. And as usual, when all cameras are solved, we then triangulate the 3D sync points. Okay? So I think it's time to show some of the experimental results. So again, we first evaluate our results on this data set with ground truth camera motion, and we compare with some recent method. We test our method with both L1 and L2 optimization. We find that, for example, on these two data sets, both methods gives very similar results, but on this data set, it's actually a more challenging case because of the repetitive window patterns that are more outliers there. So in this case, the L1 method outperforms the L2 method significantly. And this slide shows an evaluation on synthetic data with weak data association. This is the particular case of 3 cameras. We generate 3 synthetic cameras and some 3D points in this space and project them to all cameras to compute the essential matrix and then to solve the reconstruction problem. We make the essential matrix between 2 of the cameras is very poor by limiting the number of feature correspondence to 10 and add significant Gaussian noise to the location of the feature points. In that way, we make the essential matrix estimation between 2 of the cameras very bad, and then we plot the position error of the cameras with respect to different amount of Gaussian noise to the feature locations, and we find our method is more robust to our previous method. And then we further compare it with Visual SFM on this data set with relatively more images. And similarly, we find that this direct linear approach is much faster than Visual SFM. Here we are maybe 7 or 8 times faster because we are using the L1 optimization, so it is a little slower than the method I described earlier. Then here we show the number of reconstructed images. At this time, the number of images reconstructed is closer with the Visual SFM, but actually we still have maybe 20-some images less, and we actually checked what's happening there. We found reconstructing more images does not necessarily mean it's a better result. We found some of the images that are included in the result of Visual SFM by a wrong camera registration because of repetitive feature correspondences. The camera is just reconstructed at a wrong location. Okay, and this is validation. Basically, we check the consistency of our result, and that from Visual SFM, we find that the camera centers and camera orientations that are rather consistent to each other. Okay, and on this particular example, somehow because of the data association between the images is weak, the Visual SFM break it into 6 different 3D reconstructions with its default parameters. Okay. So to summarize, I have talked about direct linear formulation for camera registration. Basically, the problem becomes very simple, just the linear equation ax equal to 0. This formulation is robust to collinear motion, and it's robust to relatively weak data association. And this simple formulation opens up new opportunities, such as we can use the modern L1 optimization to deal with noisy data. And I think there are other opportunities. For example, we might think about the drifting problem. Well, conventionally, drifting problem can be measured by, for example, the covariance matrix of the camera center locations. When the covariance is large, we know probably there's drifting. But with this new formulation, we can think about drifting happens when this linear equation is insufficient to determine x uniquely. And we have other techniques to analysis drifting, such as, for example, condition numbers, eigenspace analysis, and so on. And we might also apply this to study the SNAM problem. We know in SNAM, a critical open problem is the so-called loop closure. Loop closure usually consists of two steps, loop detection and the loop optimization. Basically, the loop closure problem is that, say, if you have a camera that moves a big distance, move for a big circle, and come back, okay, if the green curve shows the true camera motion, then what you get from an incremental system is usually this red curve, okay? So we need to somehow detect that there's a loop and then optimize the red curve, somehow drag this red curve to the true green curve. So usually this involves some nonlinear optimization and is a little bit complicated for real-time performance. But with our formulation, it's very simple. A loop closure is just one more linear equation in the linear system. It won't cost too much additional computation time. Thank you for your attention.
Any other questions? Okay.
So when you construct the triplet graph, then is it possible that these that the measurements are being somehow overcounted depending on which triplets you choose? Because when you have highly dense, basically you have a lot of matches between the cameras. There are essentially a lot of triplets, and if you count how many times each camera gets included in a triplet,
right,
they vary, right?
Right.
There may be like a central camera which overlaps with everybody.
Right. Right.
So, is there some sort of overcounting when
we have a scheme? Actually, there's some details I didn't include in the talk. Basically, we have a scheme to select sufficient triangles to define the constraints. Yeah. Basically, we're going to count how many times a camera has been included in the linear equation. We limit that number. Otherwise, the equations are going to be unbalanced. Yeah.
Okay.
Yeah. Yes.
You show 8x speed up, which is very impressive.
Thank you.
But I thought it might be even more because you're not doing any nonlinear optimization. There's no relinearization. There's no bundling. There's
we still do a bundle adjustment. Let me come back to this. Yeah, so we only exclude, actually, firstly, we exclude the time for feature matching and epipolar geometry computation.
Okay.
Yeah, the time we have here is mostly building the linear equations. Mm-hmm. And actually, we did some filterings of the feature tracks. Like I mentioned, we, for the triplet-based method, we need to select the triangles.
Right.
Here, we need to select the feature tracks.
Okay.
Yeah, we need to choose the best feature tracks.
Is there any possibility of normalization?
I think so. The outlier, the feature track selection can be easily parallelized.
But the solving
the solution of the linear equation for that part, I'm not sure. Yeah.
I have a question about the data association. So you said, so one of the things is, one of the pros is it works in weak data association. But have you conducted any experiments where the data association is perfect? Because the midpoint algorithm that you solve assumes this perpendicularity constraint between A and B. In perfect reconstruction, that is 0. You will not be able to get your constraints for the midpoint algorithm to construct those M matrices if the reconstruction is perfect. Is that true?
Firstly, I think that usually won't happen. Even your data association is perfect, your feature location won't be perfect.
That's true.
That means there's, usually that 2 lines almost level coplanar in 3D space. And I think even they are coplanar, the midpoint algorithm is still valid. Basically, the midpoint algorithm is trying to parameterizing the two lines and try to find a point on both of the lines and collecting that 2 points, requiring the collection is perpendicular to both lines. That's the midpoint algorithm. But I forget to mention that we use the midpoint algorithm to compute the scale when there's 2 cameras and 1 thin point. We actually cannot use it for the case when all the vertices are cameras. Because if we use midpoint algorithm for that case, then it will become degenerated when the 3 cameras are on the same line. The midpoint algorithm is degenerated if the triangle is a line. Yeah. But we can use it for a thin point because usually a thin point won't collinear with the 2 cameras that can observe it. Yeah.
Any other question? Well, if not, let's thank our speaker once more.
Thank you.